So I want to tell you the story today of the Webb Telescope, James Webb Space Telescope, and incidentally, the history of the universe and sort of some ideas about how we got here from the beginning.
The James Webb Space Telescope, JWST, represents one of humanity's greatest achievements in space exploration. As a technological marvel, it has been designed to peer deeper into the cosmos than any previous observatory. Launched in December 2021, the JWST is the successor to the Hubble Space Telescope, but with far superior capabilities, especially in its ability to capture images in the infrared spectrum. This feature enables it to detect objects and events obscured by cosmic dust or distant in space, which were previously hidden from our view. JWST's primary mission is to study the universe's oldest galaxies, revealing how stars, planets, and cosmic structures have evolved over billions of years. Its immense resolution allows astronomers to study celestial objects, from distant galaxies and star-forming regions to exoplanets in far-flung star systems, in unparalleled detail. One of the most significant breakthroughs achieved by the JWST is its ability to observe planets within our own solar system. Despite being designed primarily for deep space exploration, its advanced instruments can also be directed closer to home, giving astronomers a new perspective on planetary bodies and events. With its powerful infrared sensors, JWST can penetrate through clouds of gas and dust, capturing high-resolution images that offer new insights into the atmospheres, surface features, and even the weather patterns of planets. This level of clarity has given scientists an unprecedented view of planets like Neptune, which resides in the far reaches of our solar system. Neptune, the eighth and most distant planet from the Sun, is a cold, enigmatic world that has long captivated astronomers. Named after the Roman god of the sea, Neptune orbits at a staggering distance of approximately 4.5 billion kilometers from the Sun. It takes Neptune around 165 Earth years to complete one orbit, making it one of the slowest moving planets in the solar system. Despite its distance, the planet's striking blue appearance, caused by the presence of methane in its atmosphere, has been a source of fascination ever since its discovery in 1846. Unlike Earth, Neptune is a gas giant composed primarily of hydrogen, helium, and methane, with no solid surface. Its dynamic atmosphere is characterized by violent storms and supersonic winds, with speeds reaching over 2,000 kilometers per hour, faster than any other planet in the solar system. For much of human history, Neptune remained largely mysterious. The first real glimpse of the planet came in 1989, when NASA's Voyager 2 spacecraft conducted a flyby, becoming the first and only spacecraft to visit Neptune. Voyager 2 provided humanity with its first close-up images of the planet and its moons, including its largest moon, Triton. While the flyby was brief, it raised many questions about the planet, particularly its extreme weather patterns and faint ring system. Since then, Neptune has remained an object of scientific curiosity, but its vast distance from Earth has made it difficult to study in detail. However, the JWST's recent observations of Neptune have brought renewed excitement and have revealed astonishing new findings. One of the most extraordinary events detected by the JWST is the recent collision of a massive object with Neptune. This event has captured the attention of both scientists and space enthusiasts worldwide. The telescope's powerful infrared sensors picked up a sudden and massive burst of heat and energy in Neptune's atmosphere, signaling an anomaly in the outer reaches of the planet. Initial observations were puzzling, but further analysis revealed that the heat and energy were the result of an enormous object, possibly an asteroid, a comet, or even a rogue planet, colliding with Neptune. The collision was so violent that it generated a shockwave across the planet's gaseous layers, producing a bright flash that was visible in the infrared spectrum. The size of the object that struck Neptune remains speculative, but early estimates suggest it could have been several kilometers in diameter, similar in size to the largest asteroids found in our solar system's asteroid belt. The impact was significant not only because of the sheer size of the object, but also because of Neptune's location. As one of the outermost planets in the solar system, Neptune lies far beyond the gravitational influences of the inner solar system, where collisions are more common due to the chaotic interactions between planets, asteroids, and comets. This makes the collision with Neptune a rare and unexpected event. One possible explanation for the event is that Neptune's gravitational pull managed to attract an object from the Kuiper belt, or the Oort cloud, two regions beyond Neptune that are filled with icy bodies and remnants from the early solar system. Another possibility is that the object was a rogue planet, a planetary mass object not bound to any star system, passing through the solar system. If the latter is true, this would represent one of the first known interactions between a rogue planet and a major planet in our solar system. Such an event would have profound implications for our understanding of planetary formation and the dynamics of interstellar space. Collisions on a planetary scale are not unprecedented. Earth, too, has experienced catastrophic impacts in its history, the most famous being the asteroid impact that is believed to have wiped out the dinosaurs 66 million years ago. Jupiter, the largest planet in the solar system, has also been subject to significant collisions, most notably in 1994, when comet Shoemaker-Levy 9 fragmented and collided with the gas giant. However, because of Neptune's remote location, such dramatic events are less likely to occur. This recent collision, therefore, represents an extremely rare occurrence, and the implications are profound. Another intriguing possibility is that the collision could have triggered seismic or volcanic activity on Triton, Neptune's largest moon. Triton is a unique moon with a retrograde orbit, meaning it orbits Neptune in the opposite direction of the planet's rotation. This unusual orbit suggests that Triton was likely captured by Neptune's gravity long ago, rather than forming in orbit around the planet like most moons. Triton is geologically active, with cryovolcanoes that spew out icy materials instead of molten lava. The shockwaves from the impact on Neptune may have triggered seismic or volcanic activity on Triton, which could be observable by the JWST in future observations. The collision also has broader implications for our understanding of the outer solar system. The object that struck Neptune may have originated from the Kuiper belt, which is home to countless icy bodies and remnants from the formation of the solar system. Alternatively, it could have come from the Oort cloud, a distant spherical shell of icy objects that surrounds the solar system and is believed to be the source of long-period comets. If the latter is true, this collision could be the first direct evidence of an Oort cloud object interacting with a major planet, offering a rare opportunity to study material from these remote regions of the solar system. The discovery of this collision highlights the incredible capabilities of the JWST, which was designed to observe dynamic processes across the universe in real time. Detecting such a massive event on a distant planet like Neptune so early in the telescope's operational life is a testament to the profound discoveries that await us as the JWST continues its mission. Scientists and astronomers will be keenly following the aftermath of this event to understand its long-term effects on Neptune's atmosphere, weather systems, rings, and moons. This collision has opened a new chapter in the study of the outer solar system, offering a rare opportunity to observe how a distant planet reacts to a significant impact. The recent collision detected by the James Webb Space Telescope, JWST, on Neptune is not only a rare cosmic event, but also a significant opportunity to understand the dynamics of this distant planet's atmosphere and ring system. The impact has far-reaching consequences for Neptune, a planet already known for its extreme and volatile weather, and it offers new insights into the nature of planetary ring systems. This chapter explores the immediate effects of the collision on Neptune's atmosphere, the potential for intensifying the planet's extreme weather systems, and the broader implications for the structure of its rings. In the days and months following the collision, scientists are closely monitoring Neptune's atmosphere for changes in its storm systems. One possibility is the formation of new storms, larger and more intense than those previously observed, driven by the energy from the impact. Alternatively, the existing storms on Neptune may become more violent, with winds speeding up and storm structures growing larger as a result of the energy injection. This presents a unique opportunity for scientists to study the behavior of storm systems on gas giants, especially those located in the outer solar system, where conditions are significantly different from those on Earth or other inner planets. Moreover, Neptune's atmosphere, with its composition of methane, could exhibit unusual chemical reactions due to the collision. The shock waves and heat generated by the impact may trigger changes in the chemical composition of Neptune's upper atmosphere, leading to the formation of new compounds or the alteration of existing ones. Observing these changes could provide valuable insights into the atmospheric chemistry of gas giants and offer a comparison point for studying exoplanets with similar atmospheric conditions. Neptune's extreme weather, which has long intrigued astronomers, could now evolve in unforeseen ways. Before the collision, the planet was already known for massive dark storms that appear and disappear unpredictably, as well as the rapid wind speeds that characterize its atmosphere. These potential changes a challenge, but the JWST's high-resolution imaging capabilities offer the best opportunity yet to observe how such rings evolve in the aftermath of a collision. By capturing detailed images of Neptune's rings in the months and years following the impact, scientists hope to detect changes in the brightness, density, or shape of the rings. Such observations could yield valuable data about the mechanisms that govern ring formation and stability across the solar system. This event also opens the possibility of observing new rings forming if the debris from the collision coalesces around Neptune, a phenomenon that has only rarely been observed. In a broader context, this collision offers an opportunity to compare Neptune's ring system with those of other gas giants, such as Saturn, Uranus, and Jupiter. Saturn's rings are the most prominent and well-studied in the solar system, but the rings of Uranus and Jupiter share more similarities with Neptune's, being faint and composed of smaller particles. Studying how the collision affects Neptune's rings may provide insights into why some gas giants have more prominent rings than others, and how external forces like impacts shape their development. One of the key questions raised by this event is whether the rings of gas giants are stable over time, or if they are constantly being shaped by external influences, such as fascinating questions about Triton's internal structure. And the recent collision on Neptune could have important implications for the Moon's geology. The massive object that struck Neptune could have triggered seismic or volcanic activity on Triton. The shock waves from the impact would have traveled through Neptune's atmosphere and potentially reached Triton, causing disturbances in the Moon's surface or interior. If Triton's internal structure is similar to other icy moons, it may have subsurface oceans of liquid water beneath its frozen crust, heated by tidal forces. The energy released from the Neptune collision could have temporarily increased Triton's internal heat, potentially triggering new cryovolcanic eruptions or other seismic activity. Observing these effects would provide invaluable insights into Triton's internal structure, particularly its ability to store and release heat, as well as its potential for harboring subsurface oceans. Scientists are keen to study Triton in the aftermath of this collision because it offers a rare opportunity to observe the geological processes that shape icy moons in the outer solar system. If new geysers or surface features are observed, it would provide direct evidence of how external forces, like planetary impacts, influence moons and their geology. Such observations could also shed light on the broader processes that govern cryovolcanic, a phenomenon found not just on Triton, but also on other moons like Europa and Enceladus. Triton's activity, especially in the wake of the Neptune impact, could help refine our understanding of how cryovolcanic moons evolve and what triggers their eruptions. The collision on Neptune also raises broader questions about the dynamics of the outer solar system and the origin of the object that struck the planet. One possibility is that the object came from the Kuiper Belt, a region filled with icy bodies that lies just beyond Neptune's orbit. The Kuiper Belt is home to dwarf planets, comets, and other small celestial objects that are remnants from the formation of the solar system. Occasionally, these objects are perturbed by gravitational history of the solar system and the formation of distant, icy bodies. Another intriguing theory involves the hypothetical Planet 9, a large planet that some astronomers believe exists far beyond Neptune. Although Planet 9 has not yet been observed, its existence has been proposed based on the unusual orbits of some Kuiper Belt objects. If Planet 9 does exist, its and modeling based on the data from the JWST could provide more insight into whether Planet 9 is responsible for this event and how it influences the dynamics of the outer solar system. This event could lead scientists to reconsider their models of the outer solar system, particularly in terms of how often large collisions occur. If the Neptune impact is part of a larger pattern of events, it could indicate that collisions in the data from the James Webb Space Telescope, JWST, and other observatories, the impact on Neptune's rings, moons, magnetic field, and the broader solar system may provide answers to some long-standing questions about how planets evolve and interact with their environment. This chapter explores the potential formation of new moons from the collision debris, the interaction between Neptune's magnetic field and the material from the impact, and how the event may trigger a reassessment of the overall stability of the outer solar system. One of the most significant possible outcomes of the Neptune collision is the formation of new moons. Neptune already has 14 known moons, including the geologically active Triton. The impact could also influence Neptune's ring system. While Neptune's rings are much fainter and less prominent than those of Saturn, they are still an important feature of the planet. These rings are composed of dust and small particles, and the impact could have added new material to them, potentially changing their structure and appearance. Over time, this material might settle into the existing rings, making them denser or altering their composition. The dynamics of planetary rings, particularly around gas giants like Neptune, remain a subject of active study, and this event may provide new data to refine our understanding of how rings form and evolve. The long-term stability of these rings is also a key question. Saturn's rings, for example, are thought to be relatively young, possibly only a few 100 million years old, and they may disappear in the distant future. In contrast, Neptune's rings are faint and more difficult to study, but the material ejected from the impact could give them a renewed prominence or create entirely new rings around the planet. This opens up an opportunity to observe how planetary ring systems respond to significant external events and how they maintain stability over time. The interaction between the collision debris and Neptune's gravity may reveal new aspects of ring formation and evolution, particularly for gas giants in the outer solar system. Atmosphere. If the debris from the impact enters the magnetic field, it could trigger new auroral activity on Neptune, providing scientists with valuable data on how the planet's magnetic field behaves. Studying these phenomena could help astronomers understand not only Neptune's magnetic field, but also the magnetic fields of other gas giants, both within our solar system and beyond. For example, Jupiter and Saturn also have complex magnetic fields that generate auroras, and comparing these planets with Neptune could lead to a more comprehensive understanding of how magnetic fields influence planetary environments. If the Neptune impact was caused by an object from the Kuiper belt or Oort cloud, It raises the possibility that other objects in these regions could be similarly disturbed, leading to more collisions in the future. Such a cascade of impacts could have long-lasting effects on the outer solar system, potentially altering the orbits of objects in the Kuiper belt or sending new comets into the inner solar system. This would force scientists to rethink the stability models of planetary dynamics. The data from this collision could help scientists predict how often impacts like this occur and what forces drive them. This has broader implications not only for the study of our solar system, but also for the study of exoplanetary systems. Many exoplanets discovered so far are gas giants like Neptune, and studying how impacts affect Neptune's atmosphere, rings, and magnetic field could provide valuable insights into how similar events might compelling case for future exploration missions. Since the Voyager 2 flyby in 1989, no spacecraft has visited Neptune, and scientists have long called for a return mission to study the ice giant in greater detail. The recent collision may provide the necessary impetus for space agencies to prioritize Neptune in their exploration plans. One potential mission could involve sending an orbiter to study Neptune's atmosphere, rings, and magnetic field over an extended period, much like NASA's Cassini mission did for Saturn. An orbiter could collect data on how the planet's atmosphere responds to the energy introduced by the impact and how its ring system evolves over time. Hot Jupiters, in particular, are of interest because they often have highly dynamic atmospheres with strong gathered from Neptune's collision could also help scientists improve their predictions of how debris from an impact might behave. For example, understanding how material is ejected into space and how it interacts with a planet's gravity and magnetic field could inform strategies for deflecting or mitigating the effects of an impact on Earth. In recent years, planetary defense has become a growing field of study, with missions like NASA's DART, Double Asteroid Redirection Test, aiming to develop techniques for altering the course of potentially hazardous asteroids. Studying Neptune's collision could provide valuable insights into the physics of impacts, helping scientists develop better tools to protect Earth from similar events.